So this partial fraction decomposition allows us to decompose a complicated rational function. To some simpler factors. That can be integrated easily. We start with a special case. When the denominator is a product of some factors, no repeated factor. And no irreducible quadratic form. So here, irreducible, I mean, if we have a following quadratic of x squared for this find the discriminant. Hey, hello, come in. Is negative. In this case, if we set this to be 0, this equation has no real root. So we say it's irreducible. In this case, all the factors are different, and there's no irreducible correcting factor. We can set up the decomposition. First, set this up, then we find the coefficients. Then we can integrate. Using the formula. Okay, so this is the first case, the easy case. Second case, slightly more general, which allows repeated factors, but no irreducible quadratic factors. If it's bigger than 1, it's repeated. Equals 1, non-repeat. Okay. In this case, we set up the decomposition. Because repeated factor to E1 times. So this will be E1 factor of this x minus x1 E1. Then we move on to the second one. And the last one will be x. Okay. We find these coefficients. Then we find the integral. So here we use another formula. If k equals 1 is what we have seen before. But if k is bigger than 1, it's okay. If we can integrate these simple functions, then we can integrate the complicated rational functions. So that's the partial fraction decomposition. The last time we had one example, the example is quite long. So I rushed a little bit and made a mistake. So let me restate the question. Okay, so that's the one we had last time, right? We want to integrate this very complicated rational functions. The denominator is square and it's cube. So we set up the partial fraction decomposition for this. The first factor, it appears twice. So there will be 2 of them. I copied it wrong. Okay, let me correct. It would be -1. X -1, A1. Then the second factor appears have the cubic power. So there will be 3 indeterminate coefficients. Okay, then through some work, we find these coefficients. We eliminate the denominator. So 1 equals the product of this. We found okay. Then the integral of this rational function is the combination of the 5 of these integrals. Even though I have more, but each of them is simpler. So we can integrate this without much difficulty. It'll be -3. Three. Two, 1. Okay. So this is the power of this method, partial fraction decomposition. We decompose something we don't know how to integrate. So a few of those that we know how to integrate. Okay, let's go over this one by one. Sakina, first one. What's the integral of the first one? Okay, now you okay, very good. You remember this absolute value. Yes. Okay, it's a habit. In the beginning, you just that logarithm, and when you become more and more familiar with it, you have this absolute value. Nice. Second one difficult. Zichen, second, how do you integrate this one?
I don't remember.
Okay, so we go over the formula. So that's our formula. So in this case, a equals 1, k equals 2. equals 2, so we have a factor over here. So what's this factor when k equals 2?
What?
So what's this factor if you plug in that k equals 2?
Oh, negative 1/2 minus 1.
Yes, okay. So we apply this formula with k equals 2, we get negative 1/2 minus 1, x minus 1 minus 1. Okay, a second. And Elisa, third one.
ln absolute value x minus 2.
Nice. Minus 2. And Sakina, this is the new one. Okay, so now you see if it's x minus 1, no power is ln. If we have power, that's completely different. So we have to use so you can say when k equals 1, have one factor, but when k equals 2, have a completely different factor. Okay. So we have to go through this. So I'm going to copy this formula. In the process, I'm going to replace the k by 2. Let me replace the k by 2. Yeah. Negative sign. Ah, not enough space. X minus 2 minus 1. And the last one.
Negative 1/3 minus 2.
Yes.
3 minus 1 times 1/, x minus 2
To the
to the second power.
yes. Okay, now let me summarize. The final result is minus minus plus. Minus minus plus 2 plus minus 1/2. Okay, so that's the integral. And you can see it's a very complicated formula. The integral of this is very complicated. That's why we spend a lot of time to do the partial fraction decomposition. Okay, it's difficult, but it have to be done. Okay, that's the second case. The third case, we allow the irreducible quadratic factor. At the moment, we assume it's non-repeat. That's the simpler case. Okay, so we'll start with some, okay, let's recall what this means. We have mentioned before, irreducible quadratic factor. If we have something like this, okay, Zichen, if we say this is irreducible, what does it mean?
I don't know. Wait, that
Uh-huh,
like
yeah, that is okay. It's irreducible. I have too many words. I forgot where it is. Irreducible. Okay. So irreducible, it means this quadratic function has no real roots. The discriminant must be negative. Okay. On the opposite side, it's reducible. It means you have the roots, have the real roots. The simplest case, we have this vector. Elisa, how do you integrate this one? What's the integral? Unmute yourself, Elisa. You are muted.
You use trig substitution.
Okay, we could use trig substitution. So if we remember the formula, and then we can use the formula, but if we forget, we can use the trig substitution. X equals tangent theta. Then this becomes 1 over secant squared dx secant squared d theta. So it will be integral 1 d theta plus c, and we go back to x, it will be arctangent. Okay, that's the first case. Second case, for this quadratic factor, we can allow x on the numerator. Okay, now Sakina, any idea? So where should we go to integrate this? X squared plus 1 and x. Zhen, what would you do? So I hear them in the earphone. Do you want to have an earphone? You can hear them. You can hear them. Okay, Zhen. If not, yes, let both of you unmute yourself. So if there's no noise, otherwise you have to mute and mute back and forth. Okay, it's your decision. Elisa, you again. Substitution?
Um, yeah.
You cannot hear it? Oh, I'm not sure why. It's I could, but it's not. Let me see if I can move this to computer. Microphone, speakers. Anything over there? Elisa, say something. Maybe I want to check if Sakina can hear you.
Hello.
Yeah. Okay, you hear something? Okay. Okay. So for this one, again, we use the substitution, but a different one where this thing will be our u. Then du will be 2x dx. We are missing 2 over there. It will be 1/2 u over u. Okay, Sakina, how do we integrate this? Du, 1/2 1 over u. How do you 1 over u? Ln u plus c. In this case, we go back to x, the 1/2 ln x squared plus 1. Because this is positive, you can drop the absolute value. Okay, the simple case, slightly more general. Slightly more general. Instead of 1, we have q squared. Where q is a positive number. Okay, let's see how could we integrate this with the knowledge over there. One. How do we go from q squared to 1? Yes. Okay. Now what do we do then?
Not sure.
So how do you? Okay. We have a q squared to make this 1. We can pull out a q squared. Then it becomes 1. Let's pull out a q squared. Q squared. And then will be x over q squared plus 1 dx. Okay, to match our previous formula, we use a substitution. This will be our new variable. U x over q du 1 over q dx. So dx q du. Now it becomes 1 over q squared u squared plus 1 q du. So simplify, it will be 1 over q u squared plus 1. Okay, so now, what about this? This formula, could we apply the formula?
Yeah.
Okay, so what's the result?
Arctan x plus c.
Plus c. Then we switch back to x 1 over q 10 x over q. Okay, so if we have a factor x squared plus q squared, then we use the substitution, convert to something of exactly the same form. If it is exactly the same form, we have the exact same integral. Just with x replaced by u, go back to x. Okay. Another change. Let's see if we want to erase this. Okay. X minus p squared plus q squared. See, we are going more and more general. This time we're going to compare this integral with the previous one. Okay, what's the difference? What's the difference between these two integrals?
What's the difference? There's the minus p part thing.
Okay, minus p. So how do we change this so we can apply the formula? What change would you make? The use substitution. What will be your use?
Wait, what? Let's like substitute another variable for x minus p.
Right. Use the substitution. Du dx. We can apply the formula. 1 over q in u q. So we apply the formula directly. Then we switch back to x. x minus q. Okay, so that's our formula. Okay, another one. See how we integrate x squared for x plus 5. Okay, so this fact first, let's check. Could we factorize the denominator? Second, check.
Yeah.
Could we factorize this?
Mm-hmm.
How you okay? What's the result?
X minus what 1 x minus 5.
If we have x minus
Oh, x plus 1. Oh no, you can't.
okay, that's good. Okay, so what do you say? And Newton's out.
I'm thinking.
Okay. So this time we tried, we couldn't do it. Then we move on to check what's the discriminant. What's discriminant? Okay, what's discriminant?
B squared minus 4ac.
So it will be -4 squared 415 16 minus 20. Oh, it's negative. That's why we cannot factorize. So it's irreducible. If it's irreducible, what do? We want to convert this to a complete square. It's something square, something square. Okay, what's this? Finish this.
Finish.
Completely the square. How do we make it a complete square? X minus 4 x plus something give us a complete square.
Plus 4.
Okay, plus 4 we get x minus 2 squared. What's the left over?
9.
It's 1.
1.
So this integral x minus 2 squared plus 1 squared. In this way, we can apply the formula we just learned in the previous one. Okay. So Zhishen, what's the integral of this?
Wait, inverse tan of x minus 2 over, x minus 2 plus c.
Very nice. So we can apply this formula with p being 2, q being 1. That's the formula. Straightforward. I'm going to change this a little bit. See what's the result. X squared plus 2x plus 5. Yes. Okay, that's fine. Okay, let's work. How do we integrate this? Could we factorize the denominator? No. Okay, so it's irreducible. Okay, irreducible. Irreducible, so what do? We want to convert this to a complete square. Okay, so what's this?
X minus 1 squared.
And what's left over?
1.
No.
Left over from what?
So we have 5. It will be something over there.
5.
So we have, so this will be x squared minus 2x plus 1.
So 4.
Yes, we're missing 4. 4 will be 2 squares.
Mm-hmm.
Now this way. Okay, again, let's try apply the formula we just learned previously. By this formula, what's the integral?
Mm-hmm.
Good one. And Alisa, what's your answer?
I can't see like the bottom.
You mean here?
Oh, you stop sharing.
Yes, so that's where we stopped. I want to continue. What's the integral?
I
Is it
can't
the
see the screen.
Oh, really? It's Jen, can you see the screen over there?
Like,
I'm circle.
no,
I can see it.
I can't see the bottom. Let's
Okay.
scroll.
Is it better now?
Yeah.
Okay.
1/2
Mm-hmm.
arctan x minus 1/2 plus c.
Yes. Okay. So that's the integral. Let's make this a little bit different. If I put in an extra factor, let me label this. This will be first one, second one, third one, fourth one, fifth, seventh. Okay, a lot of examples for this. X squared minus 4x on here. Okay, let's integrate this one. Do we use the same method, complete square, or do we use substitution? It's a check. Where should we go? Substitution or complete square?
Putting a square.
Okay, so that's a good try, but after you try, eventually you will go back to the substitution. That's because we have a difference. This is the x squared. We have x over there. Let's try. If we set q equals b will be 2x minus 4. 2. Oh, that's good enough. So we want to make up. Oh, I've got the dx. We have x over there. We can multiply it by 2 and divide by 2. Then we can with minus 4, we add 4. We separate it out. This will be 1/2 2x down. We need 2x minus 4, but only a given 2x. So I will make a 4. Then I will split this integral. I will split 1/2. First, look here. second part for now we can integrate them separately. So the first one is a substitution. 1/2 u over u. Second half 4/2. 4/2, and we copy the result we had over there. We have integrated, so we can copy the result. And now the first one is easy. We know it's logarithm. And the integral of constant. Switch back to x. X is x squared plus 4x. We could drop the absolute value because the interior is always positive. You can see a small change of the integral of this function, a big change of the result, much more complicated. Okay. So this is about the quadratic factors. Next, let's do a partial fraction decomposition with irreducible quadratic factors. Okay. The following 5 over partial fraction decomposition. And we have the obvious factorization. Decompose this to x over a quadratic factor. The quadratic factor we should have bx plus c. Because the degree is 2, this is 1 less, degree becomes 1. Okay. Then how do we find this coefficient? What method should we use? What would you do the first step?
I don't know.
Let's get rid of the denominator. I'm going to multiply both sides with this factor. If I multiply the left-hand side by this, I get 5. Multiply the first term by this, we cancel the x, left with a. And the second term, multiply by x, only x space. Okay, let's extend. We get ax squared minus 2ax 5a plus bx squared cx. So we have the equation 5 equals a plus b. That's fine. Okay, let's compare the coefficients. Coefficient. Okay, Sakina, what's the coefficient of x squared on the left? On the left.
On the left,
Uh-huh.
0,
And the coefficient of x squared on the right?
a plus b.
0, a plus b. Okay. Coefficient of x on the left.
What?
The coefficient of x on the left side.
0.
Okay, there's no x, so it's 0. And on the right, what's the coefficient of x?
Negative 2a plus c.
And Elisa, the constant term on the left.
5,
On the right,
5,
that's 8. Okay, so now we'll compare the coefficients of a system of equations. I'm going to find A, B, C from them. Okay, Sabina, which one is easiest?
5a.
Okay, so what's A?
1.
This implies A equals 1. Okay, so then next, which one would you go?
Which one would I go? What?
The two equations left. We know A equals 1.
Oh, the first one.
Correct?
Then
Okay, so what's B?
negative 1.
And Elisa, how do you find C?
C is negative 2.
Okay, let's try to be careful. Okay, I know you can do it, but just be careful. So C
Oh, wait.
will be okay.
2.
Yes. Okay. Yes. Okay. C is 2a. Okay. So this is the partial fraction decomposition. So let's summarize. On x equals a 1 over x b. The bx will be negative 1. Okay, so as long as we can decompose the integral into simpler terms, then we can integrate them one by one. Sometimes it's not easy. It takes a lot of work, but it can be done. That's the key point. Not easy, but can be done. More important, this can be done by a computer, by some program. So what the mathematicians is we figure out a way to solve the equation, then we let the machines do the repeat the work. We do the creative work, we give them a formula, and then the machine do the tedious work. Okay, so let's have 5 minutes break, and we will be back at 51. 5-minute break. The 3 cases, and now come to the last case. We allow repeated quadratic factors. Repeated reducible quadratic. Again, we will use the partial fraction decomposition. But let's first see what are the integral of the special cases. A repeated irreducible quadratic factor. Okay, let's think about it. How do we integrate this one? Elisa, any idea where we should start? We have this factor, x squared plus 1. Substitution, so what would you pick for x?
X squared plus 1.
Huh? So
Sure.
here we use the trig substitution. Okay, which one would you pick?
And
Okay, that works. Tangent. If we use this, it will be secant square at theta then square. And this will be secant square d theta. Okay, cancel two of them. And secant is 1 over cosine. So this will be cosine square. Okay, now it's let's recall, how do we integrate this cosine square? What method do we need? We use the substitution. Because this is even power, we use this double angle formula, reduce the power by half. The double angle formula, it's okay. Then we integrate. So it's 1/2 theta. Integrate, fine. How do we go back to x? 1/2 theta. Theta is that easy. Tangent. How do we convert sine to theta? The tangent to x. So this time we use the double angle formula again for sine to theta. Sine equals some work. We want to convert this to something raised to tangent. For this purpose, I'm going to divide everything by 1. That's the same. Complete trigger. Divide by 1. Then I will switch this 1, use the trig identity. Cosine square, sine square, trig identity. Then I will divide all of them by cosine square because I'm shooting at tangent. The tangent of divide all of them by cosine square. Denominator it becomes 2 tangent. Now we have what we want for x. It will be 2x. So we can switch back to x. Another one. Repeat the factor but with x on the numerator. This time we use the substitution. U equals x squared plus 1 du x t 1/2 u squared. So the negative 1. the two special cases. Now you know what happens if you have the higher power. You have a cubic power, then it will be the force. Again, we use double angle formula. We have it twice. But the integral will switch back to x. If you have a cubic power, this will be cubed, that will another 1/2 squared. So the steps to deal with complicated rational functions. First, we use the partial fraction decomposition to decompose it to a collection of simpler ones, something like this. Then we integrate the simpler ones using the method we learned before. Okay, so this is the fourth method, partial fraction decomposition. Next, we're going to extend our notation of integral. Previously, we defined the integral to think improper. Previously, we considered the following function x. We assume this is continuous. Then it's integral. The integral is defined as the limit when the partition goes finite. I don't get there. Let's check. I'll check. And this is what we call the Riemann sum. Another very famous mathematician, Riemann sum. So the integral is defined as the limit of approximation given by the Riemann sum when the partition was finite. That's how we define the integral. Then we introduce the fundamental theorem of calculus to find the integral closely to find the antiderivative. The fundamental theorem of calculus reduce this task. Reduce this antiderivative. It connects the two operations, derivative and integral, with fundamental theorem. We don't have to find the limit anymore if we can find the antiderivative. Okay, so this we'll call this a proper integral, continuous on a closed domain. Now we're going to extend this. First, we will allow infinite domain. Then we'll allow not the continuous at some point. So improper. The first case is on unbounded domain. We want to define the integral. Okay, so it's still continuous. So this time we define as the limit. We still start with a finite interval from A to B. We just let this upper bound go to infinity. If the limit how we define the int on an infinite domain. We define a limit with an increasing upper limit. If this exists, then we call this. Let's check. Check into one minute. Okay, so this is a second step that works. So under this integral runs infinity. We will check if we can find the integral from a to b for finite b. 1 to b 1 over x squared. Yes. Okay, so what's this? 1 over x squared. How do we integrate it? Again, 1 over x squared. Which formula? If it's x logarithm of x squared, a different formula. It's negative 1 over 1 to 3. It will be negative 1 over b 1 over 1. If we simplify, it's 1 minus 1. Okay, now let's check what's the limit as b goes to infinity of this integral. Zichen, what's the limit? I use this now. I'm not sure if it. I mean, that's easy one. Give the result. Okay, so for this integral, we find the integral from 1 to b, and we check the limit exists. In this case, you see this one is integrable from 1 to infinity, and the integral is the limit. Okay, let's follow the same logic and check the integral 1 to infinity 1 over x. Okay, so what do you get? Check and Lisa and start work. How do we do this improper integral? Lisa, where do we start? Maybe because let me adjust my screen. That's why I cannot see Sophia. All right. Okay, Sophia, sorry about it. I didn't adjust my screen. I didn't see you. Okay, Sophia, you okay? Let me check with Sophia. Where do we start, Sophia?
You do ln.
Okay, so again, we start with the finite interval 1 to b 1 over x dx. We now x 1 to b. It will be the difference b and y is just 0. Okay, so that's the integral on the finite interval. So what's the limit when b goes to infinity? Sophia.
It's 0. No, it's
Mm-hmm.
It's
So So not overthinking. So it's not a tricky question. Think about the graph of this logarithm function.
0? No.
Goes bigger and bigger. So the graph of this tells us this to be infinity. So in this case, we see, sometimes we see infinity, sometimes we see does not exist, or it diverges. So for this one, divergent. Let's call this one convergent. Okay, so that's the one side of the integral from a to infinity. The other side is similar. We want to define the integral. And that's a tricky one. Tricky. Zero to infinity. Constant x dx. So here, if we start from 0 to 2 pi n cosine x dx. If so with this, we get sine x 0 to pi n sine 2 pi n sine 0. So this will be 0 minus 0 to 0, and the limit n goes infinity. Is 0. However, this does not imply the integral exists. The limit along a sequence exists. Does not guarantee the limit exists. However, if we choose a different sequence, 0 to then plus output cosine x dx. Sine 0 plus one minus 0. So now can see we found two limits. The first one around 2 pi n, you get 0. Second one around 2 pi n plus 2, you get 1. So around two sequences, two different limits conclude this limit does not exist. Thus, this integral minus 0 right. Is divergent. Another example of divergent improper interval. This is the new case. Next. For this improper integral, can define it as the limit of a equals to negative infinity. Again, if the limit exists. With one side infinite interval, and the more general case, two sides. Okay, so this we will break it at an arbitrary point. if for so this is very tricky. We consider the improper integral from negative infinity to infinity. We can break this into two improper integrals, both one direction infinite. If both of the two exist, then we say this is integral, it's converted. Why it's tricky? Let's see the following. It's a very simple function. X. We want to check if this integral converges or diverges. If we choose the limit, okay, let's find that. Okay, let's do the work. How do you integrate this one?
Mhm.
X dx.
So 1.
Integral, not derivative.
Oh. Sure.
Integral of x.
Oh, x
Okay, partially correct.
squared, and then 1/2.
Yes. B squared into b squared, which is almost 0. For n and b, this integral is 0. But we cannot conclude this limit, this integral is 0.
Mhm.
Because we have to check the two one side limits. Let's check the one side limit. 0 infinity. So this one, we check the integral x dx. This will be 1 squared. If we take a limit equal to infinity, it's easy to see this. If infinity always it does not exist. It's not a number. From here, we conclude this is divergent. This one again is divergent. Even though the restriction on a symmetric domain is convergent, the overall integral is divergent. So be very careful about this. Sometimes it's convergent, sometimes it's divergent. Okay, let's try to find the integral of this e to the negative x, this infinity. How do we determine if it's divergent or convergent? Okay, Sophia, what would you do?
You make it integral of v
Okay.
0.
Okay, could you give me an antiderivative for e to negative x?
E to the power of negative x
And
and
coefficients.
negative.
Yes, yes. So that's how we find antiderivative. First, we get something almost correct. there will be corrections. Negative x, if you take a derivative, there will be a negative sign. Cancel that, make this negative. That's then what's this limit? When exponent infinity equals negative. If we look at the graph of exponential function, when the exponent goes to negative infinity, it becomes smaller and smaller and smaller to approach zero. So this converges to 1 minus this 1. So the limit exists. Then by the definition, this integral is convergent. And it converges to 1. Examples of this integral, another one. 2 sides infinity. Okay, let's try to find this if we grant it. This function x is 0 is 1. X equals the integral represent the total area on the graph. Okay, Sophia, where do we start? How do we find this area? Two side. For this two-side integral, we have to check if both sides convergent. So let's break this into two sides. First part, here's infinity. Okay, for this, again, we will start from 0 to b. 1 plus x squared dx. Okay, the antiderivative for this, 1 over 1 plus x squared.
Inverse.
Arctangent. Inverse this 0 to b goes to b. Arctangent to b. Arctangent 0. This is 0. Arctangent b. Now let's think about the limit. What's the limit? Elisa, what's this limit? Unmute yourself, Elisa. So this one we call the tangent is defined there, pi over 2. Arctangent is the flip of this. It approaches pi over 2 when b goes to infinity. first we conclude this part convergent. The second part. Again, we start with finite interval. Let's go with A. Similar will be 0, A, infinity. When A goes to negative infinity, and then A. In the same way, so we go to the negative infinity for arctangent. This way go to parallel 2, this way go to negative parallel 2. So we have a negative sign, this will go to parallel 2. So both are convergent. This also convergent. Go to parallel 2. Then by the definition, the two being convergent, so that this one is convergent to the summation. First part we checked the parallel 2. Second part we also checked another parallel 2. The result. The meaning of this integral is that the total area on the graph of this function is pi, even though it extends to both sides, it has a finite total area. So this is for the unbounded domain. In the same way, you can define if it has a singularity. For example, we may have the following function. This if Bfx is defined as the limit. We pick an intermediate point. Goes to B from one side. This is the second type of improper integral. And so we'll have a little bit more about this next time. Then we'll move on to chapter 9 about differential equations. Okay, we'll stop here.
Okay,
Any
thank you.
questions? And wait for me, I have some.
Oh, okay. I have to go though. Can I just take it?
Okay.
Thank you.
Review this. Okay.
Yeah.
Okay. You can, the questions you can ask me next time.
Okay.
Okay, guys. I'll see you on Friday.
Thank you.
Thank you. Here's your.
Oh.
I can't find the button.
Here,
One
at the
second.
bottom of its wing.
Thank you.
Okay.